happy with the arrangement, with the consultations? I thought about it a lot, and then it is impossible to talk the whole class. Maybe it was just one or two sessions. It won't be convenient for everyone to attend. So, and we just have got 3 more labs to go. And I think 3 more. 2 more, is it? We have pulse shaping, we have pulse shaping, synchronization, and channel estimation and equalization. 3 labs. So you've done 3 labs so far. There are in total 6 labs. And sorry? That's what you thought, is it? Okay. So there are 6 labs that that completes the system design from end to end. So yeah, we'll see how it goes. Okay guys, did you attempt the question that I had yesterday on multipath power delay profile? Silence. I don't think silence is golden will apply here. Please try to attempt the problems that I give you in a certain lecture, and when you make an attempt, you will have questions to ask. If you don't attempt it, then it's hard to discuss further on any of your doubts. So I came prepared. So I've got the solution today, but yep, in future try your best to attempt these questions so that we can discuss. Okay. Any questions before I get started? Okay. All right. What was our discussion from yesterday? We talked about the multi-path power delay profile being the important characteristics in determining whether a certain channel will induce frequency selective fading or frequency flat fading. We also talked about another frequency domain parameter called spaced frequency correlation. So what spaced frequency correlation tells us is the level of coherence or correlation experienced by the transmission in two frequencies. So if they are very similar, if they are highly correlated, then that's a part of the coherence bandwidth. The first point where the correlation is out by 50%, say for example, it is defined very similar to the normal bandwidth definitions we have. So if we say that a certain transmission passes through a channel and these two frequencies differ by more than 50%, then that's the point where it is decorrelated and the coherence bandwidth stops there. So that's the idea of coherence bandwidth, and coherence bandwidth is the Fourier transform of multipath power delay profile, and the first equation here captures that relationship between the spaced frequency correlation with the multipath power delay profile. And the correlation is a function of frequency lag, delta lag, which is the difference between two frequency terms, F2 minus F1. Okay? So this is the theoretical definition for frequency correlation. And we want to extract an important parameter called coherence bandwidth from the from this definition. So coherence bandwidth is defined in different ways in different textbooks. One popular definition is it is inversely proportional to the 5 times the RMS delay spread, coherence bandwidth. So there are others which say 90% correlation, but this is the definition based on the 50% spaced frequency correlation property. So if we have coherence bandwidth defined based on this, we have 1/5 times sigma RMS delay. So does anyone remember what this quantity was? This is to do with the power delay profile of the multipath channel. But what is sigma RMS delay? RMS delay spread. So this is the quantity that defines the severity of multipath propagation. So how strong the multipath components are, how spaced they are. So these things are well captured in one parameter called the RMS, root mean squared delay spread of the multipath channel profile. So in general, the multipath channel profile is a measured quantity. We do the experiments, extract measurements based in a certain channel condition, and record the received signal strength over a certain period of time based on a certain transmission. And the multipath components, the strong signal strength that is concentrated at if it is concentrated at certain time instance, they form the multipath components. So this is, for now, let's just take it as it's a measured quantity. It's not given to you. So say, for example, it's an urban environment for deployment. This is the profile. No, that doesn't work like that. You have to conduct experiments and measure the maximum delay spread. When you transmit a small, very high frequency pulse, what is the first arrival time and what is the maximum delay with which the last reflected pulse arrives? So that measures the maximum delay spread and how many multipath components are received in between. That will form the multipath power delay profile. Okay, so this is completely empirically based measurements. So it's more a practical technique that is used in determining a certain profile for the multipath propagation. So given that, say, for example, roughly if you can define multipath power delay profile for a certain environment, then we can understand from the RMS delay spread quantity calculated from the profile whether that particular channel will induce frequency selectivity on the transmission. Okay? So the frequency selectivity is important for us. Why? Because our receiver processing will depend on the effects of the channel. So if it is frequency selective effect, then you have to implement an equalizer to compensate for the effects of the channel. So frequency selective channels are also called as channels that induce memory in the transmission. So what it means is a certain transmitted pulse is received as a superposition sum of the previously transmitted pulses, of course scaled by the multipath components. But it is going to be a superposition sum of the previously transmitted symbols, and that is why we refer to frequency selective channels as channel with memory. And to compensate for the effects of the channel, we need to implement an equalizer. So the length of the equalizer will depend on the severity of the multipath channel. Severity of the multipath channel in the sense that how long the delay spread is, how strong these multipath components are. All right? Based on this, we looked at an example yesterday. Say, for example, we are given a certain well-behaved exponentially decaying power delay profile. This is a very nice, intuitive sort of a multipath channel where the where the path that arrives after a very long time decays more. And it decays as a exponential function, exponential decay, which is good. But there are other channel profiles that can be unpredictable because the component that arrives a bit later can have a stronger power compared to the one that's received earlier. So that's another type of a difficult channel to deal with. But if you have an exponentially decaying power delay profile and you want to find out from the equation or the expression whether that particular channel will induce a frequency selectivity on your transmission for a given bandwidth. So the signal bandwidth, the channel profile together will be used in deciding if a transmission will experience frequency selectivity or not. Clear? No? Yes? Clear? Yes. It is clear to few people, but at the back, do you want me to repeat or is it not clear? Hey, repeat. Repeat. That's a good start. Okay, what do you think is a bit confusing at this point?
Like the relationship of the power delay profile.
Okay, the power delay profile is represented as R delay tau. It is a function of delay. Okay. So tau is going to decide if there is a multipath tap in the received signal or not. If there is some power, say for example R of tau is equal to exponentially e to the power of minus tau by gamma, say for example. And at tau equal to 0, it is maximum. So that the signal that's received at tau equal to 0 with this profile will have maximum received signal strength because the channel is 1. And then the channel move tau to a higher value, take it to infinity. What happens to the power of the channel? Decreases. So what does it become eventually? 0. Yes. So it is going to be asymptotically approaching 0. So what it means is the channel has no multipath components at infinity. Tau equal to, when the delay is so large, then there is no multipath components coming in. So the reflected signals are not there after a long time. So that's what the profile means. And the multipath characteristic itself is not going to be like a continuous with respect to delay, isn't it? There may not be any signals received for a long time and then there is one. So it doesn't have to be existing for all time. Although we are representing it as an exponentially decaying power delay profile for all tau, it doesn't mean that there is multipath signals coming in for all delays. It is only going to occur at discrete delays. But given this as the profile, what is the RMS delay spread? So we said RMS delay spread is going to capture both the mean value of the delay spread and also the mean squared value, the power, the strength of the multipath components and the spread of the multipath components are both captured in one quantity called RMS, root mean squared delay spread. So sigma RMS delay is from this famous equation where we have mean squared value, the second moment, minus the mean excess delay whole squared, right? For exponentially decaying power delay profile with e to the power of minus tau by gamma, we ended up with gamma being the RMS delay spread. So based on that, I gave you an exercise to do in the last lecture. What it asks for is, say for example, instead of gamma, I put a 5 there, e to the power of minus tau by 5. So that's the exponentially decaying channel we have. So you know the RMS delay spread is going to be gamma. So since gamma is the RMS delay spread from the previous expression, we have gamma equal to 5, and I've defined in this example as 5 microsecond. Okay? So the 5 microsecond is substituted here, and the power delay profile is equal to e to the power of minus tau by 5. Substitute 5 into the coherence bandwidth equation to calculate what the coherence bandwidth is, basically. Can you see that? What is the coherence bandwidth in our discussions? In the context of our unit, we're going to fix this as the definition for coherence bandwidth. There may be a few others in the textbook, but this is what we are going to take. Okay? 1/5 sigma RMS delay. So if you know RMS delay spread, 5 times of that, invert it, you get the coherence bandwidth. Okay? So the coherence bandwidth is 40 kilohertz. What does coherence bandwidth mean?
So this is the threshold below which it would be frequency flat or above which it will be frequency
selective. Say, for example, if I ask a certain application requires you to transmit at 100 kilohertz as the signal bandwidth. So would that transmission experience frequency select? I might even twist the question and ask, does an equalizer is an equalizer required for 100 kilohertz signal transmission in this channel delay profile? Yes. So you would require an equalizer to compensate and recover the information. So that is why we have understood how a channel power delay profile has an impact on the frequency selectivity, and how calculating the coherence bandwidth can tell us whether an equalizer is required or not in the transmission. That is one thing. And as I just explained, these multipath signals are not going to be there for all delays. For tau equal to, it's not like for every delay there is a component. Say, for example, you're deploying, you're analyzing a channel in a rural environment where there are no big reflections, but there is one big building somewhere that would cause a multipath propagation. So there may be only just 2 reflections, but it may get reflected. The delay spread may be long, but there may be only 2 components arriving with certain delay between the 2 components. That's a possibility. So this is what we have shown here. It's a 4-path multipath channel. Each path arriving with different signal strengths. The first path is so attenuated that it is arriving at minus 30 dB power level.
less than that? No?
Slightly less, but yeah, just just for now. 30 dB, it's easy for calculations. Okay, so that's the figure I drew, but it is minus 30 dB. Okay, it's easy for us to say, otherwise it's hard to tell. Slightly less, but yeah, minus 30 dB. The second tap is second path is after 2 microsecond delay. And that's arriving at minus 20 dB. So it's slightly higher. Is that a possibility? Is that realistic? The path that is arriving later is having a higher power level compared to the path that is it possible? What could be the reason for that?
If the delay part is kind of so attenuating.
Yes.
It depends on the length it has traveled, because the
That's
longer
true.
the length, the more will be
Attenuation. Then it should be an exponential decay. Why is it like that? The path that is arriving last after 6 microsecond has minus 10 dB attenuation compared to the first path without any delay.
But does it, like this delay doesn't, I don't know how to say it. Like, it's not necessary that that particular signal
Yes.
has traveled like a long path. It
Long path.
must have been transferred later,
Yes.
and that's why it is delayed. By
Well,
6
multipath propagation is coming from once the signal SFN is out in the propagation environment,
and then
multiple reflections. So SFN is the same, but it is arriving at different y's. So y of n plus delta 1, delta 2, or tau 1, tau 2, and tau 3, something like that. So the reason could be something like the material properties of the reflector. So if it has reflected off material that absorbs more than the one that has less absorption quality, then that's quite possible that, you know, the path that is coming later has more power than the one that has just arrived.
Could it be because of the direction of the alternating?
Possible, yes, that's true. So yes, that's an advanced level of understanding where the antenna related aspects, where the directivity of the antenna and all these things can play an important role in the how multipath propagation. But this is, I mean, even with, this is true, the material properties will play a key role even with, for omnis. So that's the reason why we have identified this as the main scenario, where the properties of the channel conditions, the reflectors, and how these things propagate can have an impact. True. If we go into the advanced level of implementation where the antenna directivity is taken into consideration, the multipath profile will be affected based on that. Okay, so we can't solve with the integral as we did before in calculating the mean excess delay. We need to have it in the discrete version. So the way we would do it is replace the integral with summation and identify the number of delays that's identified by k, and tau k delay is used for representing delays at different k's, and the power associated with each tau k is p of tau k. All right, and this will give us the mean excess delay, and the mean squared value of the excess delay can be calculated with tau k squared. So these equations have a similarity, so that's why I have put them together. Finally, how would you calculate the RMS delay spread for this? So we have 4 taps or 4 paths: tau 0, tau 1, tau 2, and tau 3, 0, 2, 4, and 6. This is defined in microsecond. So substitute that into the equation for mean excess delay and mean squared value of the excess delay to calculate the values. So it is the first delay multiplied by the power in linear scale, please. So it's given in dB. Generally, the power is defined always in dB scale. With respect to the signal transmission, we have the attenuation is shown here for the multipath taps. But you need to calculate the linear version and substitute it into the equation. So when you do that, you get these two values and you end up with a RMS delay spread of 1.28 microsecond. Okay? And there could be something like a question like, you know, I might give some, this could be a part of a bigger question where we end up with a certain signal bandwidth requirement to achieve a certain performance criteria. So this is the target bit error rate. So this is how much bandwidth you can use to, you need to get a certain signal to noise ratio to meet certain target bit error rate. So that is constrained. Then, do you need an equalizer? So this could be an extension to that problem. Okay, guys? So don't be surprised if it comes like a 10-mark question where everything else is together. So, yeah. But I will give you this equation. Don't remember this. RMS delay spread calculation. If I ask you in the exam, I will put that. There won't be a separate formula sheet, but all the required formula that you need are given with the question. Okay? So you don't have to remember. But I probably won't give you like the process required for calculating an optimal solution. Taking the partial derivative with respect to something, even if you give me that indication for the arriving at a solution, that's still a correct thing. Okay? All right, let's move on. We covered for equalization least square criterion. So least square technique to estimate the channel and also equalize. But the more famous solution for equalization is one that is based on minimum mean squared error. Instead of using the observation vector and trying to optimize the equalizer vector based on that, what MMSE does is we have, it minimizes the distance between the equalized signal and the true value, x minus the estimate. So the true value minus the estimated value, mean squared error. So the error between these two is minimized given an optimal solution for the equalizer. G defines the equalizer vector, and if you know the optimal solution for the equalizer, you will be able to estimate x hat that would give you 0 error or minimum error. Okay, so we will solve this problem very similar to what we did before. It's an optimization problem again. Expand the mean squared function xm minus gm star y squared. So, and take the partial derivative of the this quantity, error quantity, with respect to every g and equate it to 0. Or whenever you see this problem, you can straight away write, use the orthogonality condition where error is orthogonal to the observation. Received is received signal and the error is going to be orthogonal. So that is the condition that you can straight away use. So you don't have to show the in-between results. Okay? So when you write that and equate it to 0, you can write the left-hand side, because you have an expectation, take G out of the expectation, and you can write it as a covariance matrix for the received. CYY times GK, and the right-hand side, Y multiplied by X star, expected value should be cross covariance or cross correlation. So use that to estimate G. So send this out to the other side, which is the inverse of the covariance of Y multiplied by the cross correlation times that's the equalizer vector based on minimum mean squared error criterion. Okay, so now this is not surprising, but let's get, it doesn't give us a lot more detail. So if we just expand this whole equation for the minimum mean squared error metric, where the estimate Sn, S hat of n, which appears at the output of the equalizer with a certain delay, Nd. So the Nd has to do with the order of the filter that you select, Lf. So since you have Lf plus 1 coefficients, the sample that was transmitted at n will appear at the equalizer output at n minus Nd, or n minus Nd is the transmitted symbol. So it will be there will be a delay of Nd units, symbol periods at the equalizer.
Choose ND that minimize the expectation.
Hi, what's it?
Choose the ND that minimize the one impacted.
Uh,
The last line, yeah.
yes.
Choose ND that minimize this expectation. Right?
Choose ND. ND, oh yes, okay. Yep, that's right. You can say that. Because choose the equalizer length LF that minimizes this error vector. So that is the criterion. So ND is a result of the choice you make for the equalizer length. So if you choose a longer length for the equalizer, it should, for linear equalization, as you increase the length, it should minimize the error.
But shouldn't it have a limit to how much we can increase the length?
Theoretically, there is no limit. But when you implement it in practice, if you use a very long equalizer length, it's just going to process too much noise, and the performance doesn't get any better, and you may even see a slight increase in the error flow. But this doesn't usually happen with the linear equalizers, which is, the scope is restricted to linear, but there are some advanced equalization principles that that feed back the estimated sequence and do the processing again. So if that happens, a longer filter may be causing more problems than actually improving. Okay? So, but let's not get into the discussion that we can't fully discuss. So if we restrict our discussion to the linear equalization, S hat of n is produced with a certain delay when processed with an equalizer coefficient f. The g's are now f's. Sorry about that. The equalization is represented by the vector f of nd. So the nd correspond to the certain length of the equalizer, causing a delay of nd symbol periods. Okay. So let's define the vector y, the received samples, for a length of LF. Okay? That's the next equation, and y of n is again expanded. What's the received? It is the channel convolved transmit sequence. So that's why H is a matrix now, which is a convolution matrix. We've seen that, if you remember the structure of the convolution matrix before, tuplet structure, correct. Well done. So it captures the effect of the channel length. The columns correspond to the,
Corresponds to LF,
length of the channel, and the all the n, which is
plus M.
perfect. So yes, that's good. So H is a convolution matrix, and S of n is the vector of transmit sequence, and B of n again is noise vector. So this is just a compact representation of the equation we've been used to so far. So we used to have a summation from L equal to 0 to L, H of L, S of n minus L for writing the convolution. We substituted for all n and all L to write up matrix representation of the convolution. Makes sense, guys? Y of n is one sample, whereas here the bold-faced Y of n is a vector of samples. Okay, similarly, the vector of S is defined over a length L. That is to do with the channel length. LF is the channel equalization length. L is the channel length. Okay, so considering the delay introduced by the equalizer, the S of n minus nd, what was transmitted nd events prior to Sn, is compared with the estimate produced at the nth time instant at the output of the equalizer. Make sense? This last equation is nothing but equalizer produces an estimate at the output at the nth time instant, say for example. And that is actually the value that was transmitted nd events prior, because there is a delay that we have to account for at the equalization stage. So we need to construct our error metric based on the error between S of n, the true n minus nd that was truly transmitted, and the equalizer predicted estimate of Sn. So that is the idea. Make sense, or do you want? Oh, well done. Oh, I've got 2 people nodding this time. Yes. Go for it. All right. So let's just now get into the details of it. We saw that the equation here for MMSE has been derived in the previous few slides. So the covariance matrix C by Y is nothing but expected value of Y of n, Y star of n. So substitute for what Y of n is in terms of matrix algebraic framework that we have defined here. Y of n is H S n plus Vn. H is a convolution matrix. Going back here, substitute that, and you end up with, take the expectation inside, and you should be able to write this equation. You will get an expected value of the transmit sequence Sn, S star n. You know what the energy of the symbols are because you've normalized it. So that's out of the equation, and you only end up with the deterministic or the H part of it. And noise variance is defined, expected value of V of n times V star of n. That is sigma V squared, identity matrix. So this is channel H transpose HC times plus the noise variance times identity. Okay? Just substitute Y of n with this equation here. Yn is H transpose Sn plus Vn inside this equation, and take the expected values and of noise and the transmit signal. You should be able to arrive at this quantity here. And similarly, you do for the Y of n, S star of n minus nd, because that was what was transmitted when we have an estimate at nth time instant. So when we do that, we end up with H transpose and a vector of E with 1 at the right point where It appears after ND events. So I will expand E of ND and write it for you in the uploaded lecture slides. So you should see a 1 at a point where you have the estimate. So it will account for the delay introduced by the channel. So there is an zeros at the start and then a 1 appearing after ND events. So that is the vector we need to write there. Okay, for now, let's just substitute E of ND H transpose for CYS into the equation, and we should be able to see a standard result for MMSE, minimum mean squared error. H star H plus noise variance inverse H star END. Now, the important part is how does it connect back with what we have derived in the past. We are inclined towards least square solution for practical reasons compared to MMSE. So if you want to know why that is important, look at the solution for MMSE at low noise with under high signal-to-noise ratio conditions or high noise variance and low noise variance. See what happens. When you have noise variance large, so this second term is significant compared to H star H. So you have sigma b squared I inverse multiplied by H star END as the result when the noise variance is high. So this is nothing but you are correlating with the channel conditions. It's a matched filter, matched to the channel. It's not the matched filter we discussed for the pulse shaping. So it is the matched filter matched to the channel. So H star would get rid of the channel condition. So that is the idea of when the noise variance is large. But when the noise is low, which is the conditions we experience in the lab, isn't it? The software-defined radio lab, you have a pretty good hardware with you, and it doesn't introduce a very high noise floor. The signal-to-noise ratio is affected, and the channel condition is like, you know, the transmitter and receiver are in line of sight. So SNR is high always for the practical implementation. You can introduce artificial noise, but that's not real channel noise. It is just the noise that you are experimenting, just like a simulation. You're increasing or decreasing noise to see how the performance changes. But the hardware introduced noise is very low. So the signal to noise ratio conditions are very high when you are doing your experimentation. So the least square solution is what results from the MMSE solution when you have high SNR conditions. So we are in effect implementing the optimal solution, just considering the fact that we have high SNR conditions in our experiments. So the noise floor is so low that we don't have to worry about noise for the hardware introduced noise for implementation. So okay, so just remember that the MMSE is going to be a matched filter when it is in the when the noise variance is high. When the noise variance is 0, it approaches least square solution. Okay, so it is intuitive to say that the complexity of the equalizer depends on the choice of LF, for sure. So any filtering operation, as you increase the length of the filter, you have to do more operations, multiplications, and additions, because it's a convolution. So the complexity will depend on LF. Larger values depend on the performance, give better performance, but higher complexity. That's another intuitive conclusion you can draw. To achieve a certain performance, you have to choose enough equalizer length. And with linear equalizers, it will keep increasing up to a point, but then after a certain length, especially after the maximum delay spread of the channel, the effect is minimal. Okay, so just a quick recap of where we are positioned at this point. So we did carrier frequency synchronization, we did time synchronization in 2 stages, and then we downsampled it, and we are after matched filtering. So that is not, that is here, GRX of n. So the matched filtering is there. After that, you did symbol synchronization with the oversampled signal, and then you did the frame sync, and then we have arrived at a signal that is only impaired by the multipath channel. So that's the equalizer is going to deal with that. The FL that we have constructed is based on the channel estimates that we did at the receiving.
The delay for the frame synchronization is still in D, right? It includes the delay because before that you only have synchronized for the single.
Sorry, what is it?
Before the ND, you only have synchronized up to a single level. So the delay for the delay that should be compensated for the frame synchronization is included in the hedge, right?
The estimates are delayed by ND. Okay, so the frame sync. So what are we seeing after the downsampling? We are seeing a received sequence Y of n. That doesn't include ND. But the received sequence is processed through the equalizer, and the estimates of what you have transmitted will be delayed based on the choice of the equalizer length. But that is something that you're doing after. You need to do the frame synchronization, extract the data portion from the frame, and then put it through the equalizer.
So we have a frame synchronization right after downsampling.
Before, yes.
Which is not included here.
It is not included here, that's the truth. That's why I was saying that, well, yes. So it is difficult to fit the whole thing into one diagram, but yes, you're right. You need to correct for, yes, straight after downsampling, frequency sync should be done. Carrier frequency offset before channel estimation should be done. If you do channel estimation with the frequency offset still in there, you're going to end up with errors. So the channel estimation should be performed after the synchronization and compensating for all the impairments. Sometimes what happens is channel estimation and frame offset compensation are combined. It's a joint procedure where you can pick up the frame start and also estimate for the channel. So if you,
I think that's the case in here.
yes, you can do the channel estimation here and the frame offset detection. But the equalizer calculation will only depend on the data portion. So you have to detect the frame start, throw away what the training sequence is, you just extract the channel state information, and from that point on, it is only the data portion that is going to be processed. So it is the, at this, the first arrow pointing upwards is going to give you the channel estimates and the frame start. That is used for processing the data that is corrupted by the channel. All right? Anyway, so then once you have processed the signal, the data portion of the frame through the equalizer, what's produced at the output should be accounted for the delay introduced by the equalizer. So it is passing through z to the power of nd hat. So it is accounting for the delay due to the equalization. What will nd depend on? Yeah,
Delay make a system of the
equalizer, yes. So ND is the, ND equal to LF plus 1, basically. So LF is the filter order, and an estimate of the transmit signal is produced with a certain delay, ND. So that depends on the choice of your equalizer length. And the choice of your equalizer length, again, will depend on the channel delay spread. So because if you have a multipath with a very long delay spread affecting many, many, many symbol periods, you have to account for compensating that length of the channel. So this is the connection. Okay, I think we ran out of time again. So what I was going to discuss is the alternative way of compensating the channel effects that is in the frequency domain. So it's called the frequency domain equalizer. And I'll upload these slides and quickly go over the information next time, because I want to get into OFDM. We are a bit behind in our in our pace. That's okay, but as long as we can make use of these consultation sessions. This week is fully consultations. Are you happy about it? Well done. So am I going to see many questions at the consultation? Well done. Thank you.
Are we having it today?
Yes, yes, yes. It starts today. Every lab session today, this week, is consultation. Next